Good morning, students. Today's topic is timing and control. Okay, so we have learned in the last class about registers, the register operations, and how the register transfer is done using a common bus. And here we are going to see how the operations of the registers, okay, that are performed on the registers are controlled. Okay, two aspects that mainly control the operations are timing and control. Okay, timing is done by the clock pulse. Okay, the timing for all registers is controlled by a master clock generator, the circuit that generates the clock pulse. Clock pulse is generated and that determines the timing the operation can be performed. Okay, at which particular time the operation can be performed. So how it is done? The clock pulse are applied to all the registers and flip-flops in the system. And this determines the timing of the operations performed, okay, on the registers. But the clock pulse do not change the state of the register unless it is enabled by a control signal. Okay, the control has to be enabled. The control signal has to be enabled by the control input. Okay, when the control input is active, and at the same time when the clock pulse is active, okay, when the clock pulse goes high, when the edge of the clock goes high, the operation is performed. Okay, the clock signal is, the two states are positive and negative, correct? Okay, here this is the low edge and this is the high edge, okay, or it is the negative side of the clock and this is the positive side of the clock. Okay, here this is the rising edge, okay, rising or leading edge. And this edge is the falling edge of the clock. Okay, so when the circuitry is made in a way that, okay, it gets activated, okay, the signals get activated when the clock pulse goes high, okay, from low to high. So this high edge of the clock activates the operation. Okay, this is the timing. The timing is determined by the clock signal. Okay, when the clock edge goes from low to high, or if the circuitry is in a way that, okay, if the operation has to be activated when the clock goes from high to low. Okay, so okay, the falling edge of the clock makes the operation done. So the timing is determined by this. But this does not change the state of the operation, only the clock pulse. Okay, where it has to be enabled. The control input also has to be enabled by the control signal. Timing is decided by the clock signal and the control input. Control signals are generated in the control unit and it provides control input for the multiplexers in the common bus, control inputs in processor registers, and micro operations for the accumulator. Okay, we have seen multiplexer input. The control inputs to the multiplexer are S2. If there are three control inputs, S2, S1, and S0. Okay, or S1 and S0. Okay, these need to be controlled. These are controlled by the control unit. Correct? Okay, so these are all activated by the control unit. These are control signals. This, if it is register transfer, the value of this, correct? It decides the, which particular register need to be selected for transfer, or if it is some other operation. Okay, if it is some other operation, okay, need to be performed. And the load input we have seen in the registers yesterday, we have seen, okay, register AR, address register. The control operations that can be performed on the register are load and, okay, LD, load, and it can be incremented or it can be cleared. Okay, these are the control operations. So these need to be activated, okay, enabled. Okay, when this particular control input is enabled, and at the same time when the clock pulse goes high, the operation will be performed. So the control of any operation is controlled by the timing of the clock. Okay, when the clock edge goes high, positive edge of the clock activates it. At the same time, when the control input is enabled. And the two types of control organizations are hardwired control and microprogrammed control. If we see this hardware controlled, the control logic is implemented with the hardware circuits, okay, such as logic gates, flip-flops, decoders, multiplexers, and other digital circuits. Okay, so the hardware logic circuits, by changing the circuitry, we can control the operations, correct? And the second type of control organization is microprogrammed control organization. Here, the control information is stored in the control memory in the form of program. Okay, it is programmed. And any changes can be done by changing the program, updating the microprogram in the memory. Okay, so these are the two types of control organization. It can be hardware control, okay, implemented by the hardware circuits, okay, such as logic gates and flip-flops, okay, other circuits, digital circuits are used to implement this control. Or it can be microprogrammed control organization, okay, the control memory is programmed to control the operations. So when there are changes need to be done, the program is changed, okay, so that controls the operations. So here we see how the operations are controlled by hardware control. Okay, in this chapter we learn about hardware control. Let's say this is our instruction code with 0 to 11 bits used for address, and the last bit for the addressing mode, okay, the 15th bit, and 12 to 14, okay, bits 12 to 14, 12, 13 and 14, the three bits are used for opcode, correct? The instruction format we already learned, the instruction code, okay, the 16-bit instruction code. The address, number of bits used for address depends on the, okay, the size of the memory, the number of words in memory. And this 12-bit address specify the address or locate the address of the memory that has 4096 words. And opcode, operation code, 3 bits. Okay, that means 2 power 3 is 8. Okay, this opcode of 3 bits are used to specify the operations, okay, on the computer that performs 8 operations. Okay, and this is to 15th bit is to determine the addressing mode used. It can be direct or indirect address. When I is 0, it means direct address, and 1, the value of, if the value of I is 1, it is indirect address. Okay, we learned about this. And here, how this operations are controlled is this opcode. The 3 bits of opcode are given as input to the decoder. Okay, here we have a decoder that takes 3 inputs. Okay, so how many outputs it generate? Decoder is a circuit that takes n inputs and generate 2 power n outputs. Okay, so for 3 inputs we get 2 power 3. Okay, so it gives 8 outputs. Okay, as this is the output of decoder, we call it as D naught. Okay, D naught, D1, D2, D3, etc. up to D7. Okay, this is the last output of the decoder. D naught is the first output and D1, D2, etc. up to D7. Okay, 8 outputs. Decoder is a circuit that is used to decode the coded information. Here opcode is coded. Okay, when it is 3 bits, it may be 0, 0, 0 to represent one operation. Okay, one particular operation. Or it may be 0, 0, 1 that represent another particular operation. 0, 1, 0 that represent some other operation. Okay, so this way 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. Okay, these are the different operations. Okay, that can be represented using a 3-bit opcode. And here we have a control logic. And this address, okay, address part of the instruction set is given directly to the control logic. So to locate the particular operands, this address is the address of the operand on which the data on which the operation is to be performed. So to locate the operand, okay, in memory, okay, it is directly given to the control logic. And the output of this decoder, okay, D0 to D7 are given to the control logic circuit. D0 to D7, okay, that represent 8 different operations. Okay, so here it is the subscript, okay, the subscripted decimal number 0 here, and D1, 1 is the subscripted decimal, and here it is 7. Okay, that is equivalent to the binary value of the corresponding opcode. So here it is 0, this is 1, and this represents 2, and this is 3, 4, 5, 6, and 7, means D0. Okay, this is D1 and this output is D2. If the opcode is 0, 1, 0, that means D2. Okay, the operation that is denoted by this D2, okay, is performed here. Okay, so it is decoded. The operation specified by this opcode in the instruction code is decoded by the decoder 3 by 8 here. 3 by 8 decoder and given as output. Okay, the 8 outputs are given to the control logic for performing the operations. And we have a sequence counter. Okay, this responds to the clock signal. And the 2 other okay, control inputs given to the sequence counter are clear. One is to clear the counter, clear, and the other one is to perform increment. Okay, this sequence counter, okay, it responds to this clock signal and it generates the timing signals, okay, for determining the timing for performing these operations. Okay, one of these operations. So to generate the timing signals, we have the sequence counter, and it is a 4-bit sequence counter. So it generates 4 outputs. And that is decoded by another decoder. Okay, this is the decoder used to decode the control signals that are generated by the sequence counter. Okay, timing signals are generated by the sequence counter that is decoded by this decoder. So it takes 4 inputs. So as the decoder takes 4 inputs, 2 power 4 is 16. Okay, it gives 16 different outputs. And the first one is, okay, it is timing signal T0. The first signal it generates is T0 up to T15. Okay, 0 to 15. So it generates 16 timing signals. And here the sequence counter, the clear operation is to clear the counter. Okay, means when the counter is cleared, okay, to 0, the value will be 0 here. It is cleared to 0. The signal generated would be T0. Okay, it generates T0. And when it is, the other operation is incremented. Okay, when it is cleared, it sets that the timing signal is cleared to T0. And when incremented, it gets incremented, okay, by 1. So T1, it generates the signal T1, T2, T3, etc. up to T15. Okay, so this is the, sequence counter circuit. When incremented, it provides the sequence of timing signals T1, T2 to T15. Okay, when cleared, it generates T0. Means the sequence counter is cleared to 0. So the signal it generates will be T0. And when this particular operation, one of this operation is linked to the timing signal, okay, connected to the timing signal. And when that goes active, when the timing goes active and this control input goes active, okay, this control logic performs the, gives signal to perform the particular operation. Okay, this is how the operations are controlled. Okay, the timing at a particular time, the operation need to be initiated. Okay, that is controlled by this clock, and the sequence counter generates the timing signals. Okay, that I will explain it with the timing diagram. You will understand it more clearly. Okay, the instruction code here, the 3 parts of instruction code: address, opcode, and the addressing mode. Okay, it may be direct or indirect address. And okay, address is applied to the control logic, okay, to get the operand, to fetch the operand on which the operation need to be performed from the memory. And opcode need to be decoded, okay, to find the operation that is to be performed. The 3-bit opcode is given to the decoder. Okay, it is a 3x8 decoder. It takes 3 inputs and gives 8 outputs. The 8 outputs are the 8 different operations the computer can perform. Okay, it is represented with by using D0 to D7. Okay, D0 means one operation and D1 is another operation. Let's say add, D1 is add. Okay, D2 is increment. Okay, and the logic, arithmetic and logic operations, whatever the operations. And the control, this is a control input that need to be active to perform that particular operation. And the timing has to be determined by the clock, right? When this particular operation can be performed. So that is done by the clock, and the sequence counter responding to the clock signal. Okay, clock input is given here. So responding to the clock signal, the sequence counter generates the timing signals, okay, from T0. When it is T0, okay, means it is the clear, okay, it's the result of clear operation. Okay, when the clear input, the control input to the sequence counter is active, it generates T0. Okay, other cases, it is increment operation. Okay, the operation performed here is the control input, INR will be active. So it generates the timing signals from T1 to T15, okay, by incrementing it by 1. And when this timing and these are synchronized, okay, the operations are synchronized, the control logic performs the particular operation, okay, specified by the opcode, okay, at the given time, okay, given by the clock. So the timing diagram, if you see, okay, this is our clock signal. the rising edge of the clock. Okay, this is the leading edge of the clock, and this is the end of T0. Okay, let's say time T0, T1, T2, T3, T4, and T5. The timing signals T0,
Ma'am, please admin 545, ma'am. Signal problem, ma'am.
5:45.
Yes, ma'am.
I'll check it. The timing signals T0, T1, T2, T3, T4, and the clear, yes. Clear control of sequence counter. Okay, let's say that the clear control of SC is positive, okay, means active at the beginning, okay. So here at this point, okay, beginning of this first cycle, at this time, it finds that the CLR input is active, okay, means the sequence counter need to be cleared and T0, right? The timing signal T0 is generated. So here T0 gets active, okay, and the one cycle, this is one cycle, okay, T0, and at time T0, okay, when it is the clear input, if you see the clear input of SC, okay, clear control of SC is low, it is not active. So that means the other operation is performed, it is not clear. Okay, first case it is active. At this point it is active. Okay, it is high, the clear input is high. Okay, so when the clear control is high, T0 is signal T0 is initiated, means it is active. Okay, that clears the SC sequence counter. The decoder here generates T0, okay, at the first stage, first cycle. And the second is at time T0, okay, at this particular point, it is low, okay, here it is low. So T1 means it is incremented, it is not cleared, it is present, yes, control signal generated is T0, it gets incremented by 1, so T1 becomes active, okay. And again, the next cycle, if you see T1, at this point, okay, it is low, the clear input is, clear control is low, it's not active, so it gets incremented and you get T2. And the next okay, cycle T2. At time T2, the clear input is low, okay, and it gets incremented by 1. So the timing signal generated would be T3 by the decoder. The next clock cycle T3, okay, at time T3 here, it is low, the clear input is low, okay, so it gets incremented by 1. It generating T4. And if you see the next cycle, okay, at time T4, the clear input is, the clear control is active here, okay, at this point it is active, okay, so it need to be cleared and the control signal T0 need to be active, okay. So here T0 get generated. And the next cycle T5, it is low, clear control is low, and after T0 when you increment you get T1, okay, the control signal T1 is active. Okay, this is how, when this timing signals are synchronous, controlled with the, connected with the operations, okay, a particular operation that is to be performed, okay, and when it is active, when that particular control is active, the operation will be performed, okay, and at the positive edge of the clock, when the clock goes high, for the positive triggered, positive edge triggered flip-flops or registers. Yes, now let's say we have the operation. Okay, the register transfer statement is written like this: T0. This is a control statement given. Okay, control function is T0, means when T0 is active, perform the operation of transferring the content of PC to AR, right? Okay, the meaning of this register transfer statement is at time T0. Okay, when T0 is active, when the control signal T0 is active, okay, when that is 1, transfer the content of PC to AR. Okay, so when this T0, when the timing signal T0 goes high, okay, when it becomes 1, what happens, the, and also not only the timing, okay, timing is decided by this control, this timing signal T0, and what, where is a PC, the program counter is the second input to the bus, common bus, right? It need to be placed, and it is controlled by the control signals S2, S1 and S0 to the bus, right, to the multiplexer. So when S2, S1 and S0 are 0, 1, 0, okay, that is 2, right? Okay, 0, 1, 0 is 2. So at when the control signals S2, when the value of S2, S1, S0 are 0, 1, 0, okay, and when T0 is active, okay, so this is how we synchronize. This clock is synchronized with the registers at time T0, when the control signal T0 is active, okay, when it is 1, and when the control inputs S2, S1 and S0 are 0, 1, 0, okay, here 0, 1, 0, the content of PC is loaded into the bus. It is placed onto the bus. Okay, at the same time, it has to transfer to register AR. At the same time, the load input, okay, here the load input of AR is gets activated, get enabled, and the content of PC will be loaded into the register AR. Okay, this way the timing, okay, of this operation of transferring not only the control signal, okay, only when 0, 1, 0 is active, okay, when S0, S2, S1, S0 are 0, 1, 0, the operation will not be completed. Okay, it is decided by the timing is determined by the clock. Okay, through the sequence counter, it generates the timing signal, and when the timing is, when that particular timing signal is active and when the control input is active, okay, both need to be active, and that enables the operation. Okay, so at this particular time when T0 is active, the content of the PC register will be loaded onto the bus, and at the other side, AR will be loaded. The load input, okay, this control to AR will be active, okay, will be enabled, and the content of PC will be loaded into AR. Okay, that's about this control timing and control. Timing is decided by the clock signal, okay, the clock pulse, and the control is decided by the control signals. One of the control signal used here is S2, S1 and S0, okay, for the multiplexers. And the other control signals used in this case is LD, load, INR and CLR, okay, that load input, when load is active, when INR is active, okay, when the INR input is active, control input is active, it increments the content of the register, or when CLR, clear input is active, it clears the content of the register.